Good morning, everybody. Yes, last Thursday I put the videos up and notes up for the lecture. So that's what we did, sections 1 and section 3. Today we're going to cover 2, 4, and we'll try to get to 5. If we don't finish 5 today, or get to 5, we'll finish the chapter next time. And then chapter 1 will be done. Chapter 1 is on your Dmat course. So if you're looking for the homework for the chapter 1 stuff, it's on the Dmat course, the 0315. Don't look for it on the Math 1314. It's on the Dmat course. All right, so that's where the homework is. Here's a review of what we did last time. Graph 2x minus 3y equals 6. By finding M and B. What does M represent? The little m represents the slope, and B represents it's the y-intercept. Such confidence back there. Typically, M and B are found in this equation. Anyone remember what the name of it's called? Can we go through all the 3 different types of formulas for equations? If not, we'll do that today. There are 3 different forms of equations. Since this is the slope, and B represents the intercept, the y-intercept. This equation is therefore called the slope-intercept formula, or the slope-intercept form. How do you get the slope-intercept form? Solve for y. So let's take this equation. First step, solve for y. What's the first thing you got to move? Okay. Would it be wrong moving the y over? Would it be wrong moving the y to the other side? No. Actually, that in a lot of instances may be the safest thing to do. Because since this sign in front of the y variable, the value is negative, it may be easier moving that over. But let's look at it both ways. So you said, let's move the 2. How do we move the 2 over? Subtract 2x from both sides. Because we have to get rid of that 2x. 2x minus 2x cancels out. Equals minus 2x plus 6. I know y'all were forced this in junior high and high school, but try never to divide by negative numbers. That will cause more trouble than anything, because the longer the equation, if you try to divide by a negative number, you'll have a lot of signs, division symbols, equal symbols, negatives, minuses. So the first thing you want to do, since that's a negative, is just change all the signs across the board. Change the signs. There used to be a -3, now it's +3. -2 is now +2. Positive 6 is now a negative 6. It's going to happen anyway, but this way is a lot easier. Always treat your signs and numbers separately. Now, all you have to do is get rid of the 3 by dividing each term by 3. And 6 divided by 3 is 2. Divide each term by 3. And before that, we change all signs. Since y is negative. Since y is negative, in front of the y is a negative symbol, so we do these guys. So now what does this tell us? What does this tell us? Can we get any information from this? Yeah, we know the slope. What's the slope? Yeah, the slope is always in front of the x. Refer back to this equation. Whatever's in front of the x is your slope. Notice my slope does not have an x on it. It's just the number in front of it. What is this to represent? The y, that's my b value. What's its location? Yeah, it's at 0, -2. Right. Yeah, it's exactly, it's just down 2. So our graph plot b, since the b is -2 on the y-axis. So -2. From that point, follow the slope. So the slope, the positive number's on top, so it means it goes up, and the bottom's always positive, always goes to the right. So from this one, we go 2 up, 1, 2, and then over 3. Connect the dots, and there's our graph. So no matter what kind of equation you have, it's always going to happen that way. Trick question. Graph that equation. What's the first step? Yeah, we have to get y by itself. So we have to add 2 first. So y equals +2. That's our entire equation. What's our slope? Remember, we are now in this form. Y equals mx plus b. Is there an x in here? No. So what number would m have to be for their x to disappear? Very good. If there's no x, that means m is 0. What's the B? Right. The constant is always the B value. The constant, once you have Y by itself, the constant is always your Y-intercept. So what's the graph? What's the graph going to look like? And don't say a line. It's going to be a line, yes. But what's the graph going to look like? Yes, it's going to be horizontal. Where? So we have a y-intercept to B. So we plot that. The horizontal line has to be through that point. Because no matter what x you give me, no matter what x you give me, if you give me 2, the point of that one has to be 2, 2. Because y is always 2. It's a constant. If you give me -3, what's the y value at -3? 2. Because y is always equal to. It never changes. So it's a horizontal line. So again, so that's if you have a slope of 0, it's a horizontal line, or if you have a horizontal line, slope is 0. It'll save you lots of time if you see that. All right, let's go on to section 2. This one talks about functions and relations. The first thing we have to do is we have to distinguish between correspondence versus a relation. And it's not by chance these words were used. Here we have in the correspondence, here we have group A and we have group B. Here we have group A and here we have group B. A, B, C. 1, 2, 3. Let's do the same thing here. What have you ever heard the word correspondence before? What do you think it means? In the old days, whenever you mailed a letter or anything to somebody else, that was called a correspondence. School in the Old West, actually, there's a lot of places in the world, we still have school by correspondence. You'd sign up for a class, they'd send you the material, you would mail them back the homework assignments, the tests, and everything like that. They'd grade it and send it back to you. It's all by mail. So correspondence would be like this. This is A. The school sends out materials to students. Okay, that's for class 1. This is for class 2, same thing. It sends information out this way. And class 3. A relation, like a relationship. If you're in a relationship, it's only you and somebody else. You hope. That's a relation. So what's the difference? Yeah, as you notice, all the lines are a good indication. You have A, which is one entity communicating with multiple entities. So it's one to many. A relationship or relation is one person to one person, one person to one person. So it's one to one, or it's more so written like this in mathematics. So let's look at this one. Let's look at this one. Here's a teacher. There's one teacher in class A. Got 3 students. Is that a relation or a correspondence? Correspondence, because you have one entity communicating with multiple entities, 2 or more. Going backwards, is that a correspondence or a relation? Why? Very good, because this one student, 2 students, 3 students, each one individually is talking to the professor. So going this way is a relation, going the other direction is a correspondence. Now, what does that mean in math terms? So if you see any of these nodes, these dots, if it has more than one sending in to more than one person, then it's a correspondence. In order to be a relation, they all have to be one to one. How would it look? There's an example of a correspondence. There's an example of a relation. I'll put one more. What's the difference? What do you mean? Well, yeah, on this one, all the Y's are the same. But more importantly, remember, it's the one professor to all the students. Let's call this one our x-axis, and this is our y, our independent variable, our dependent variable. Because in order to draw, we would find a point, we have to pick a value for x, plug it in the equation, that gives us y. So this is a correspondence because this value of x and that value of x are the same. Are the y values the same? No. So what that means is you have person 2 communicating to 2 different people. So it's a correspondence. This one, it's a relation because going this direction, this person only speaks to this person. So it's a relation. And this is a correspondence. So what rule would we look at here? You guys were correct looking at the X and Y's. So how do we put it into words? Like for this side, if all of the X values are different, then it is a relation. Because if all the X values are different, then there's no way they could overlap. But if two X values are the same, the Y values must be the same to be a relation. So if two X values, the 2 and the 2, if those two are the same, in order to be a relation, they have to have the same Y values. If they don't, then it's a correspondence. Here's a 2, there's a 2. The Y's are the same. So that's the same point. So that's actually really what you're looking at is if the X's are the same, the Y's better be the same. If all the X's are different, then by definition, it's automatically a relation. That leads us to a test. How would we know if it's a relation if we look at it graphically? Let me show you. Let me put here we have 5 functions. I thought it was pretty cool when I was showing this class the other day. It's pretty cool. I can make out a word out of it by using these same. I had hope spelled differently, but I said let's make a word out of it. So, which one of these follows that rule about being a relation or a correspondence? Is the first one a correspondence or a relation? Why? So, what does that mean? What does it have to do with our rule we just had? Yes, you remember the rule, but do you remember why we got the rule? Yeah. It goes with what you said. If we pick a value of X, let's say that's 1, and we draw a vertical line, what do we notice at these 2 points? What's this location here? That one is 1, 2. What's this location? 1, -2. You have the same X's, but different Y's. So this is a correlation. Likewise with a circle. Same thing there. This is a correspondence. Oops. not a relation. Not a relation. Is the next one a relation? If we draw a vertical line anywhere, there's no other point. There's no other point. So this is a relation. Because for any vertical line we draw, any x value we pick, there's only one y value that it corresponds to. How about the cubic function? Same thing there. Any vertical line we draw, we only get one point of intersection. That's called a relation. How about the last one? Yeah, same thing. Because any vertical line you draw, it crosses it only once. So that's how it goes with our definition. If for any x value, it corresponds to one and only one y value on that graph. It corresponds to one and only one y value on the graph. We call this the vertical line test. If I give you a function or a picture and you draw vertical lines anywhere, will it cross the graph only once? If it does, then it's a relation. If it doesn't, it's not a relation, it's correspondence. Vertical line test is vertical line test. Any vertical line through the graph will only intersect at one and only one point. That's what the vertical line test is all about. And that's what we eventually call a function. It's an equation that has a 1-to-1 relation at every point. That's what we call a function. I know in high school and junior high, when you first learned about functions, you would see something that looks like this. Your input. Your input is usually always your x values. We call those the independent variable. The reason it's called an independent variable is because it can be anything you want it to be. You put it inside here. It goes through some equation, let's say 3x plus 2. So you put in a value, let's say x equals 3. That's your input. That's your package you put on the input. In place of x, you put the 3. So 3 times 3 plus 2. 9 plus 2 equals 11. And out comes your output, which is 11. And that's what y equals. Y'all seen this before, this kind of picture before? There's Channel 13 used to have cartoons like this for kids on Saturday mornings many years ago. So to differentiate between the equation y equals 3x plus 2, which is that's what's our traditional equation. Whenever we deal with functions, we have a special way of writing it. You notice the equations are the same. It's just what they equal is different. They look different. It's the same values, but they just look different. So let me go back to here. So what we're saying here is y is the same thing as f of x. They're the same thing. If we had a point on our graph, it's xy. When we deal with functions, we represent them like this. To be honest with you, this is more definitive what you want to do. The letter f as the function name. Whatever's inside the parentheses, that's the variable in the equation. Whatever goes in here goes in place of all the x's in the equation. Goes in place of all x values in the equation. It's red. F of x. That's how we read it. It actually means the function f with variable x equals blah, blah, whatever the equation is. rest assured that y and f of x are interchangeable. This is true. Whenever you see one, it means the other. Got it? So in the old ways, this is how we would have to write it. The equation y equals 3x plus 2. Well, find the value of y when x equals -2, x equals 0, x equals 3. So what you'd have to do is A, B, C. So A would be y equals 3, x equals -2. And we solve it. Positive times negative is negative. 3 times 2 is 6 plus 2. Opposite signs, 6 is larger, so it's negative. 6 minus 2 is 4. So what does all this tell me? What does all that mean to me? What does it give me? We just finished working this stuff. What does that mean? Now for B. For B, x equals 0. So anywhere I see an x, I put a 0. Three times 0 is 0. 0 plus 2 is 2. When x equals 3. Positive, positive is positive. 3 times 3 is 9. 9 plus 2 is 11. So what do these find for us? What good are they for us? What can we do with them? Actually, what do they represent? They're points on a line. In order to see what this means, what was happening here, we'd have to plot all these. So this first one, what's the point of the first one? Nope. What was the x value we put in there? We put in -2. The y value is -4. So we'd plot that point. In this one, we plugged in 0. Actually, that's what it tells us up here. X is 0. Y is 2. The third one, y is 3. X is 3. Y is 11. So those are the 3 points. So whenever we do this kind of stuff, whatever we put in, whatever we get out, that represents locations of a point. A lot of extra writing. Now, if we did functions, the way I would represent the same stuff here in functions, they mean exactly the same thing. Whatever's inside the parentheses is my x value, right? So the first one, x is -2, so that's what x equals. Instead of having to write something like this where you have to backtrack everywhere you go, this one, all you have to do is match this name with that name, and here's your function. So we know x, anywhere seeing x in there, we put a -2 and then work it out. The rest is the same, so. But it's all right there, it's compact. This one, here's the name, it means 3x. Anywhere I see an x, I put a 0. And then likewise. So first off, functions are a lot cleaner to use. There's less writing. You don't have to put this whole legend up here. Whatever I want, I can put inside there. Another cool thing about functions. With functions and equations, you can combine them. So y is equal to 3x plus 2, z is equal to -2x. Find this equation if x equals 2, or when x equals 2. When x equals 2. So what would you have to do? Yeah, first I'd have to find y equals 3 times 2 plus 2. That's 6 plus 2 equals 8. And then I have to find the other one. Z equals -2 times 2 is -4. Once I define y and z, I plug them up here now. Y is 8 minus 3 times z. Two times 8, 16. Negative times negative is positive. 3 times 4 is 12. 16 plus 12 is 28. With functions, once I define a function, it stays defined as that until I redefine it or cancel it. I don't have to have this whole second section here. Does order of operations still apply here? Yeah, was we have order of operations to do the special operations. This is a special operation. It says, go to the function f, anywhere you see an x, plug a 2. So I'll come up here. 3 times 2 plus 2. Anywhere you see a g, put a 2. That's -2 times 2. 3 times 2 is 6. -2 times 2 is -4. Negative, positive. Functions allow you just to keep on going straight down. You don't have to go back and forth and write one number here and then plug that somewhere else. Just go here. Can the x values be different? Let's look at the first one. We'll still use the same equations. Find 2y minus 3z when x equals -4 and x for this equation equals 3. This is where it gets complicated. I can have different values of x for each function. So I first find this equation when -4. So we have 3 times -4 plus 2. Positive times negative is negative. 3 times 4 is 12. 12 is bigger, so it's negative. 12 minus 2 is -10. So it's 2 times -10. What is z? Now when z is equal to -2 times 3, positive negative is negative. It's -6. So you see, I mean, whenever you use these kind of literal equations, you have to jump around a lot. Take this equation, work it out, and make sure you put the right number in there. -20, negative is a positive. 3 times 6 is 18. 20 is bigger than 18 is negative. 20 minus 18 is 2. The rest is the same. But in functions, I don't have to go out and make a separate rule for each equations. I just tell you right here what I want the values to be. This one, go to the function f. In place of x, put a -4. This one, go to g. In place of x, put a 3. And then we work it out. So functions are a lot more practical to use. I can also, in functions, and this will be a discussion we'll have later on, we'll have what we'll call compound functions, Fog and Goff. So you can't do this with those. All right. Everybody okay with this? Any questions? How many functions are there? Wrong. There are 12 basic ones. Everything else from there builds from those 12. Well, I'm giving you. Yes, please. I just take one pass around. Yeah, there should be enough for everybody. What I'm giving you is what's called the library of functions. So on the very bottom, you can put library of functions. We're looking at the first page. We're looking with the one that has a C on the right-hand corner. So on the very bottom of that page, put library of functions. In high school, they call it the parent functions, which I thought that was ridiculous because you only have 2 parents. There are 12 of them. How can that be? Yeah. Yeah, this is, yeah, it's true. This is 21st century. So let's look at the 12 basic functions. A constant function, because we're also going to talk about something called domain and range. Anybody hear that before? What's a domain represent? Very good. Domain represents all values of X. Actually, all possible values. Because sometimes you can't use all of the X's. You can only use a certain subset. And the range, all possible values for Y. Yeah, we'll find them later on. All right. So let's look at these. A constant function. By C, I mean some number. Let's say Y equals 2. What would that graph look like? Y equals 2. So horizontal line, yeah. Because there's no X values in there. If there's no X, that means it's a horizontal line. It goes through 2, Y equals 2, and it's a horizontal line. So what's the domain of a constant function? Nope. What are the possible X values? Are there any restrictions to X? Yeah. Notice this arrow here. It keeps on going forever and ever. It goes towards what number? Negative infinity. And likewise, going this way, it goes to positive infinity. So it goes from negative infinity to positive infinity. Or instead of writing that, we can just write this little symbol here. That symbol there stands for all real numbers. So they're synonymous. Is that R looks like a realtor sign, means any number from negative infinity to positive infinity, all real numbers. What's the range of a constant function? What's the Y values? Yeah, it's just whatever the value is. It can't be anything else. We'll go to this side. A linear equation. Now we have an x. Once you see an x in an equation, you know it now moves. It's no longer horizontal. It now goes up and down. Actually, the x value tells us a lot about what the graph's going to look like. This equation, when x equals 1, y equals 1. When x equals 0, y equals 0. When x is -1, y equals -1. So that equation is a 45-degree angle line through the middle, through the origin. What's the domain of that one? Okay, when we look for domain ranges, look for domains, are there any restrictions? Can x be negative? Yeah, -10 makes y equal -10. Can x be 0? 0 equals 0. Yeah, that works. Can x be positive? So if it can be positive, negative, and 0, then that means it could be all real numbers. You could write whichever one you want, and both mean the same thing. I'm putting both in there just so you can see it. How about the range? Can the answer be negative? Range goes with which axis? The y-axis. So at this point, there's the y value, y value. Where is it going towards? It keeps on going forever. Towards what number? Negative infinity. Likewise up here, where is it going? To positive infinity. So this is the same thing. The absolute value function. What does absolute value really mean? What does it do? Right. Whatever number you put in there, positive, negative, or 0, comes out positive. So if I put 0 in there, I get 0. If I put 1 in there, I get what? Positive 1. If I put positive 2 in there, positive 2. So this side goes on forever in that direction. If I put -1 in there, what do I get? Positive 1. Very good. If I put -2 in there, I get 2. So I get this graph. What's my domain now? Well, no, the domain of the x values. Look at all these. From this graph, I can keep on going all the way down. So it goes all the way to negative infinity. Likewise, this way, I can keep on putting numbers in there to positive infinity. So it's all real numbers. How about my range? Well, look at the y values. Can it be negative? No. Can it be 0? Yes. Can it be positive? Yeah, look at the graph. If you draw a horizontal line, that's the y values. And they keep on going to where? Positive infinity. So the y values start at 0 and goes on to infinity. it looks like this. Bracket this time. If you can use the number, then we put a bracket. The greatest integer function. A lot of people have never seen this before. Another name for it is called the stair-stepper function. The greatest integer function of the int command. What it does, it truncates. It just drops off any decimals that you have. So there is no decimals. Whatever's in front of the decimal is your answer. So when x is 0, y is 0. When x is 0.5, it's 0. All the way to 1.0, then it jumps to 1. It stays that way until it gets to 2.0. Then it jumps to 2. Then that goes to 3, and that jumps to 3. And likewise, the same format on the other side. You can say it rounds down. That's the greatest integer function. So what's the domain? Now, this keeps on going forever and ever, both directions. So what's the domain? Right. Negative infinity to positive infinity. Because all of the x's are allocated. Where this one stops, this one starts. Where this one stops, this one starts. So there's always an x value. Now we get a little bit different. What's the range going to be? What are the y values? It's only the integers. There's no decimals. So for there, we write the letter n, like that. Next class, I'll give you the full list of them for integers, real, quotient. I won't have time. I won't go there just yet. So what this means is all integers. That's what it means. All right, the bottom right-hand corner. Quadratic equation. If you're not sure about a number, always just plug in some numbers. Positive, negatives, and 0. 0 squared is 0. Very good. 1 squared is 1 squared is 1. 2 squared, 3 squared, that's all up there. Negative 1 squared, yeah, negative 1 squared is negative 1 times negative 1, which is positive 1. Negative 2. So this is the first of our curves. It's called a parabola or parabola. What's the domain? Can you put negatives in there? Yeah, if you put negatives in there, it just becomes positive. Can you put zero in there? Yeah, zero. Can you put positives? So that means it's negative infinity to positive infinity. It's all real numbers. There are no limitations which you can put in there. What's the range going to be? Looking at the picture. Can you have negatives? No negatives. Can you have zero? So you can have zero. Where does it stop? Yeah, it goes all the way up to positive infinity. It goes all the way up. But remember, since it can equal zero, we put a bracket there. The cubic function. Can x be negative? Yeah. So if I put negative 2 inside there, what do I get? Negative what? Negative 2 cubed is negative 2 times negative 2 times negative 2. Negative times negative is positive, times negative is a negative. 2 times 2 is 4, times 2 is 8. So when x is negative 2, y is negative 8, all the way down here. When x is negative 1, negative 1. When x is 0, 0. When x is 1, and when x is 2, positive 8. So this graph looks like this. On this page alone, we had 3 of those 5 letters I had in an earlier graph. Remember his counts? Here's the u. The cubic function, if we had a further equation, it would look something like this. That's a cubic function. But all we have is x cubed, so it looks like that, like an S. What's my domain? And we did the constant function, that's our t. What's a domain? Because x can keep on going as far as you want to. How about the range? Same thing. Very good. All right, turn the page. Now, these top 2 are called the inverse functions of the last 2 we just did. The radical. Radical simply means that square root symbol. It can have anything in that V area, any radical, the nth, it's called an nth root. An nth root looks like this. Where that number right there is called the root. The reason we call it square root, because there's an invisible 2 right there. What that 2 tells us, you have to have 2 of the same number to take it out of that radical. For example, square root of 4 is equal to what? Why is it equal to 2? Because 4 is made up of 2 times 2. Once you have 2 of a kind, it comes out. So that's basically the function of a radical. If I have a cube root of 8, I need 3 of a kind now. 8 is made up of 2 times 2 times 2. Since I have 3 of a kind, it becomes 2. That's how radicals work. Knowing this, can x be negative? Well, can you take a square root of a -4? Can you give me the same number multiplied together that gives -4? -2 times -2 equals +2. +2 equals +4. So you can't take a negative. So you cannot have negatives in there. Can they be 0? Yeah. So when x equals 1, y equals 1. When x equals 4, y equals 2. And when x equals 9, so it looks like this. It's a curve, a slight curve. What's the domain? Very good, 0 to infinity. Since 0, I can use 0, I put a bracket there. How about the range? What's the smallest number I can use? And it goes up from there, and it's a bracket. Cube root is a little bit different now. Because now, since it's cube, it can be positive, negative, or 0. Right. So when x is 0, y is 0. When x is 1, y is 1. When x is -1, y is -1. When x is -8, y is -2. When x is +8, y is 2. So this graph looks like this. The domain and the range. Yeah, all real numbers. Same with the range. Any questions so far? We got 4 left. The rational. Whenever you see the word rational or see a fraction, that's what it means. Rational means ratio, which is a fraction. Can x be negative? Yeah. Can x be 0? No, you cannot divide by 0. Can x be positive? Yes. The bigger x becomes, the smaller the number becomes. 1/10, 1/100th, 1/1000th, 1/1,000,000th. So the bigger the x becomes, the smaller the number. So this graph looks like this. I can get up to very close to 0, but I can't touch it. When x is 1, y is 1. Anything else from there changes. Likewise on the negative side. When x is -1, y is -1. We just cannot use 0. Think of that. We cannot use 0. So what's my domain going to look like? Always start from the smallest. What's the farthest left I can go? it goes on forever, so it's negative infinity. And it goes very close to zero, but doesn't touch zero. So I put a parenthesis there. Notice there's a difference between the radical. If I can use zero, I put a bracket. If I can't use it, I have to put a parenthesis. On the other side, can I use zero? No, so it's zero with parenthesis, and it goes all the way to positive infinity. Since it could be either side, we put the U for union. So what's my range going to be? Yeah, from negative infinity all the way up to zero, but I can't use it. And then from zero, which I can't use, to positive infinity. This other one, well, we still have class. Remember, we have 2-hour class today. We're here for two class periods, so I'm not going to stop. I'm going to stop after I finish this, but that gives me I'm going to have a leeway to go 2 hours if I need to. So don't start putting stuff up. What does this square here mean? What's going to happen to this number? Or what's not going to happen to this number? What's that? Anybody? Whenever you square a number, will the answer be positive or negative? Always positive. So in other words, with this one, our answer can never be negative. We're never going to have a number down here. So when I use negative x's, I can use from negative infinity all the way up to zero, but I can't use zero. And then likewise for the positive, I go very, very close to zero, but I can't use zero. It's like the Atari symbol. So what's my domain? What's the smallest x can go? Negative infinity. So on negative infinity all the way up to, can I use zero? No. And then the other side, I start at zero, which I can't use, so it's parenthesis, and I go all the way to positive infinity. Now the range, since we can't have negatives, can we have zero? No, it gets very close to it, but we can't use it. Then it goes on positive infinity from there. Now we have the exponential functions. Exponentials is where the x is the exponent. I mean, up until now, we've always had x, then it raised to a number. These are exponential functions. Which means no matter as, and b has to be greater than 1. B can only be positive greater than 1. Which means we'll never have a negative answer with these. Well, unless there's a negative in front, but by itself, never. It always, always, always crosses through 1. And it's an increasing function. It's like an airplane taking off. So the domain is from negative infinity to positive infinity. The range, you can't get to zero. Only positive numbers greater than zero. There's a whole chapter we're going to deal with on exponentials and logarithmic equations, chapter 5. So just know what the graphs look like, and that'll be a start. And logarithmic equations are the opposite of exponentials. Because they're opposites, that means they cross through one on the x-axis and look like this. So the domain is, it can't be negative. There are no x negative negatives. Can't be zero. So it's going to be positive values of x. And the range is all real numbers. Put these to memory because we will have quizzes throughout the course about these, because the faster you memorize these, chapter 2 will be easier because we're going to do transformations. I'm going to give you a function. You have to know basically what it looks like. And then from there, we'll take. I'm also next class time, I'm going to talk to you more about these. So you can look at any equation you have, and you can tell the basic shape of the function. But we'll do that next time. Any questions? Oh,